Hello everyone. In this work we looked at the problem of acoustic unit discovery, where we want to learn discrete representations that resemble the phonetic inventory of a language. And we want to do this in a fully unsupervised way. In other words, we want to learn this just from unlabeled speech audio. Self-supervised learning have recently been used to tackle this problem, where you would, for instance, try and reconstruct an input signal, as in the case of a variational autoencoder, or you would want to discriminate between future observations, as in the case of contrastive predictive coding. And in both of these cases, you would use an intermediate vector quantization or VQ layer to discretize the input. These models work quite well on a number of tasks, such as phone discrimination, but they still don't exactly mimic the phonetic units. So to see that, here we've got some speech input with the human level annotations there at the bottom. And here we've got the encoding from a VQ-VAE model. And we can see that the VQ-VAE encodes the speech at a much higher bitrate than the phonetic sequence. And we wanted to address this problem. So we proposed the Vector-quantized segmentation algorithm, or VQ-Seg. So in a standard VQ layer, an encoded feature vector would be assigned to some codebook entry. And that decision of which code to use would be taken individually for each of the features. In VQ-Seg, we basically assign blocks of adjacent features to the same code. And the problem then becomes, how do we actually segment that input into blocks so that we get a good segmentation of the input? And to do this, we optimize a sum of squared distances. So we're basically trying to find the segmentation which gives us the smallest sum of squared distances of those arrowed lines in the figure here. So this might be one segmentation, and this might be another one. And we find the lowest cost segmentation using dynamic programming, where we also include an additional penalty term that encourages longer segments. We apply VQ-Seg on top of two self-supervised models and evaluate the results of 4 tasks: phone discrimination, phone segmentation, word discrimination, and then word segmentation. The VQ-Seg algorithm gives reasonable performance compared to other approaches, but importantly, it does so at a much lower bit rate than other approaches. Just to see that qualitatively, here we've got the codes from the VQ-VAE again, and then if we apply VQ-Seg on top of this model, then this is the implicit segmentation that we get. In future work, we would want to investigate even deeper whether and how these VQ-Seg units represent phonetic units.